start again. The main reason for putting this picture in your packets anyway was just to indicate to you in a rough sort of way how the thinking has been going and what has happened to that kind of thinking. Most of this comes from the 60s, this kind of network analysis. Okay, and at that time, and before that time, kind of beginning with Hebb, we started to see the dismantling or the deconstruction of the behaviorist school of psychology. Okay, so now you recall those two bars that I drew. One is the perceptual interface, the other behavioral interface. And the behaviorists weren't interested in what's in that black box. And so they just never ever looked at it. And since they dominated psychology, including the idea that Skinner is at Harvard, or was at Harvard, and Skinner was one of the major protagonists of the field. And so even at the level of Harvard University, they were producing primarily behaviorists. So there were relatively few people, out there thinking in a different way. Well, fortunately enough, there's Britain on the other side, they didn't have such a hardcore behaviorist attitude. And there were other people in this country also that knew that black box meant something, and so started going into it. Well, again, they always knew that there was networks in there. That's certainly nothing new. And they tried to model it by virtue of these simple diagrams that I've been showing you. And this kind of a network just indicates one way in which you can get a difference in the transfer of information from one network to another, from one piece of time to another. And generally speaking, that I of k, which I call information, I sub k of t, that I call information, nowadays, because everybody's thinks digitally, is a snapshot in time. So it's not actually time, but rather a snapshot of time. And it's just constant snapshots. And usually, k, in the sense of modern complexity theory, usually goes in integers, 1, 2, 3, 4, like that. And then the weights of these wires in this diagram, each one of those are also a function of time. So at snapshot 1, it might look like this, and in snapshot 2, neuron 4 might fire, whereas neuron 1 might not. Okay, and then you get a different configuration. Okay, and then in that way, you are able to transmit information from one side of this network to the other side. And the information changes with each snapshot you take. And that's what the meaning of all these weights here are, is that they change in time also. Okay, now, that's one of the major problems of modern complexity theory, is that, when you get into the neural network chapters of the complexity theory books, they will always give you these rather complicated neural network functions that are digitally conceived and are functions of time only. There are no space coordinates. Okay, so that what you're faced with is digitally changing the weights, digitally changing. Now remember, if you don't have space coordinates, there is no difference between 2 inches and 2 light years in distance, because it's not a function of distance. Everything is instantaneous, and everything happens just as soon as you specify Okay, the T is 1 or 2 or 3. It's all instantaneous. That's the network configuration. So it is literally, digitized in that peculiar sense. Okay, now in complexity theory, even given that, they have come up with all kinds of different ways of looking at networks. There's all manner of different ways. And they have even come up with, for example, this one, which is kind of the classic, this thing. Okay, that's been, in foundation theory, that's been renamed the V-disk, which is variance disk. And that's what I refer to it as in the literature. Okay, this V-disk is one of the earlier renditions of a neural network, particularly. And the reason that it is a neural network, and the reason they drew it this way, is because if you start going into complexity yourself, or you start doing mathematical models of neural networks, you come to the conclusion rather rapidly as you think about it, that if you've got this thing here, this structure that's got so many neurons in it and so many wires coming out of those neurons, that it must be the case that every neuron within a certain vicinity has got to connect to every other neuron. I mean, how could it not with that kind of density and that number of wires? It would be really kind of bizarre if you didn't have that kind of a situation. Okay, so that what they came up with to accommodate that notion that every neuron has to connect to every other neuron is this picture. Okay, now this only has 10 neurons in it, but you'll notice each neuron has a wire going to every other neuron. And it's easily depicted this way. Okay, it's from this particular picture, when you use the notational scheme, depicted in this thing, that notational scheme, you can generate mathematical functions that will start to explain what's going on here. Okay, and it's from this picture and from those mathematical functions that you derive that gives you the concept of like 6 degrees of separation, between all the human beings of Earth, plus a few other assumptions that come from sociology. But from this is where that idea of 6 degrees of separation comes from. In other words, everybody in this room knows Kevin Bacon, and Kevin Bacon somehow got to be the guy that we're all separated from by 6 degrees. But if we track our friends back, our relatives and our friends, we trace it back, we cannot be more than 6 degrees away from anyone. And that's been pretty well established that in general that's pretty much the case. Now, does that apply to the Aborigines in Indochina or something? Well, that's a question, but it pretty much applies to everybody else. We're so interconnected. This, in a way, this is the way human beings are, societies of human beings. Yeah, anyway, it's from this picture that came from. Now, in the sense of foundation theory, this thing is used in a different way. And we'll be getting to that way in a little bit. But keep this in mind because this is kind of a classic way of depicting a network. And this is kind of and still is, still the classic way of notating what it is that you're doing. Whether you call the weights, whether you call them W or not, it doesn't matter. Whatever you call it, this is the way they usually do it and keep track of everything. And if you even apply that method to this, it's a fairly nifty way of notating what's going on in something even this complicated. Okay, now, now what we want to do is, since we already know that we have some problems that arise in the digital solutions in the digital world, you know, as to the problem of, for example, recognition and identification, etc., those kinds of problems, which are much more simple than altruism and acquisitiveness, etc. Since we have those kinds of problems already there, and since in complexity, what we have is a situation, complexity in general, what we have is a situation is that the mathematics of complexity is even more complex than complexity is. It's a nightmare. You know, it's ridiculous. It's one of the most ridiculous fields I've ever seen, because everything is summation symbols. Nothing is an integral. You know, there's no infinitesimals, etc. You know, and so I was, you know, and I went through the complexity textbooks and all of this kind of stuff, and I'm looking at this, and oh my God, why are these people doing this way? And I understand why they're doing it this way, and I understand why they're doing it this way, but nevertheless, what I didn't understand is, well, why aren't they putting the geometry into this deal? You know, in other words, there is a difference between 2 feet and 1 feet. You know, 1 foot and 2 feet. There's a difference. And nature takes care of that difference. And they already know that nature does that with regard to long distances. If a neuron has to, if a nerve spike has to travel a long distance in a biological creature, the way that happens is this. If this is our tube of spaghetti, and there's a nerve spike traveling along here, just as indicated in that nerve diagram, that nerve spike diagram that I gave you, what nature does, if it has to travel any long distance, is it takes this tube and it coats it with a myelin sheath. It's called myelin. Okay, and that myelin sheath, anyway, causes this thing here, now this structure coated with that myelin sheath, to transmit the potential. Oh, and by one other thing, every so often on a myelin sheath, it breaks. It breaks into sections. And these things you can look up in any neurobiology textbook. But those breaks, are those little bumps, those are called the nodes of Ranvier, R-E-N-V-I-E-R, I believe. Okay, those nodes are important, but they're fairly long distance apart. What happens electromagnetically is this voltage potential, and remember, it's locally created by the opening and closing of those gates. It isn't actually moving. Okay, it gets to here where the myelin sheath is, and let's just extend it a little bit more to make the picture look kind of right. Okay, and the neuron is, let's say, ordinary neuron over here. It's transmitting this thing, and it hits this sheath here. Now that sheath has now shut off those voltage-activated gates that would ordinarily transmit the signal. But what this does is this acts like an electromagnetic conduit, so that at field speed, the speed of the transmission of field, and I call it electronic speed, you know, like the speed in copper as opposed to the speed of light in a vacuum. But at field speed, it transmits to this node of Ranvier, where it is recreated in regard to how fast do the voltage-activated gates open and close. Well, they're in the millisecond range. So your nervous system operates in that millisecond zone. That's how fast nerve impulses move. You wouldn't describe them in the microsecond zone. On the other hand, when it hits one of these myelin sheaths, it now becomes a conducting device because it's like a coaxial cable now. You know, and it's got those cable properties of having, and it's not going to transmit by virtue of opening and closing of the gates anymore because of that sheath. So it transmits electromagnetically at field speed, the field speed in that medium. Obviously it's not copper, but it's still, you know, it transmits at a fairly high speed. The impulse then reappears at this node of Ranvier. Okay, now this is a voltage impulse, so that field transmits down to the next, recreates it, down to the next, and recreates it. Okay, and then finally it comes out of the myelin sheath and then starts going around normally again. Okay, nature takes care of that distance by doing that. The other thing that nature does, and this is apparent in the Aplysia snail. Now keep in mind, the Aplysia snail is a pretty big device. It's a sea creature, and it's fairly large. You know, it's kind of the whale of all snails. And that thing has also some very long propagation distances to take care of. And the way that, and we do too, for example, from here, our fingers to our backbone, we don't have a gabillion neurons, you know, from here to here every so often. We just have one, or not one, but I mean, you know, one neuron will take care of certain areas of your arm. And they're rather very, you know, they're really long. They're like a meter long. Okay, and they have myelin sheaths on them, those things. Okay, in an Aplysia snail, the way nature takes care of it is it makes the tubes. This is like a tube of spaghetti. Looks like spaghetti on the outside, but it's hollow. Okay, and the way nature takes care of it in things like Aplysia is it makes it larger. The diameter of the tube is larger, and that speeds up the propagation. And that's because you have more voltage-activated gates going on. Okay, now, and in addition to that, the electromagnetic properties of the cable properties of a coaxial cable that size are different from a coaxial cables that are real small. I mean, it's the same functional thing going on, but, you know, if you want to call it that, resistance is different. Okay, given that those kinds of things are apparent, you know, when you get into the neurobiology, and if you read neurobiology textbooks, it's obviously apparent to the neurobiologists. But for some reason, the complexity theory people are not picking up on the idea of putting in, okay, nature is doing this, so let's duplicate nature, and instead of having, you know, this thing like, instead of having these functions like this, which end up being extremely complicated, you know, why not make a function like this? That goes to why not do that instead? Okay, now one of the reasons why they don't do that is because, boy, the way they do complexity, that would really get, I mean, it's pretty ugly, dirty, rotten as it is. But if they did that and then still kept no differentials, no analytic solutions, in other words, boy, would that be a mess. Okay, so there needs to be some other way of looking at this in order to get around these problems of complexity theory, and in order to get around the problems, then the corresponding problems of neural network theory, because those just become unmanageable after a while. They can get to some real simple solutions, like these, you know, things like, you know, this kind of network solution that, you know, applied to more complex networks like this. That results in stuff like barcodes, the ability to do barcodes, you know, and the computers are fast enough to be able to read those things. You know, Fred Myers has a check out yourself kind of a deal. You know, and you notice though when you're checking out that the computer has to take some time to read those things. And you put it in there, you put your milk, and I'm a milk addict, you put it in your bag and it weighs it, you know, was that the right product? And that takes a little while to think. It has to think for a while. Okay, now we, since that is the case and since that becomes a bottleneck, the mathematics becomes a bottleneck, and correspondingly there, all of those calculations have to be carried out by the computer that you're using. That becomes a bottleneck because these equations are truly, truly ugly. I mean, you know, I have a complexity textbook, you know, they'll list, they'll give equations that'll cover 1 or 2 pages using every letter in the English alphabet and every letter in the Greek alphabet too, you know, with subscripts, you know, and superscripts. My God, they're unbelievable. But there are certain people who like that stuff. You know, I don't want to meet any of them, but they.
And there's chaos there.
Anyway, so it came time for me anyway to start thinking about this in a different way. Okay, now here we start focusing in on a different way to look at this problem. There's certainly nothing wrong with the way they have been looking at it, but that's a particular way of looking at things. Okay, there are other ways of looking at the same problem, and the way I kind of like to look at anything, you know, is to compare it with nature. I am a theoretician, but I nevertheless do an awful lot of observation, and I try to appreciate whatever it is that I'm seeing. I try to see it. You know, in other words, I'm very aware that I could have been raised in a vertical environment. So I might not be seeing horizontal lines. I don't know that. If I can't see them, how am I going to know that? I don't know of their existence. It's the same thing with the patient, same way with the patient, you know, MC, the neuropsychology patient. MC who was blind. They fixed his eyes, now he can see, and he can't handle the information, he can't handle the new world. He can't see horizontal and vertical either, because those feature detectors, so to speak, those operational amplifiers aren't in there, in his brain. So he can't handle it, and kills himself. Okay, anyway, we've got to look at this in a different way then, and so the way I do it, one of the ways that I do it is I sit on my porch down there in Casila, and my sister has a tree over there, and and then she has a deck in which she feeds the birds, lots of, bird feed. Okay, so that in the springtime, those birds, geez, there's millions of them in this birch tree. And these are little snowbirds, and they come flying into this birch tree, which by now is fully leafed. They come flying in there full blast, land on a branch, check out the surroundings, and then go down there to the feeder and start chomping on all the goodies down there. Okay, now the point is, though, is they fly right into that birch tree with all of the stuff around, and they never crash, they never hit anything. Now, on the other hand, later on in the summer, all of the new chicks, they get kicked out of the nest, and they're going to go to the same tree. Well, they do crash. Every once in a while, they'll crash. Or they'll run up to one of my flower boxes and crash on the leaves. They'll crash on some of the string because they haven't quite yet learned how to fly. But they learn. And then after they learn, a little later on in the summer, they're all back running right through that tree, right through it, or right to a branch. And they're doing it, like that. They have to. They have to be making decisions. The brain has to make decisions just pretty much instantaneously almost in order to be able to do that. And that's been a marvel in the animal sciences and biological science for a long time. The other thing that I observed is that we have bumblebees and wasps and other insects, that I have flowers and stuff that I put in these boxes that I built, and there's lots of flowers. Okay, so bees come up to them, let's say, because bumblebees are something that everybody has a picture of. Well, we have them up here, and they come over to this flower. They kind of scout around, sniffing out everything they can, all this stuff. And they see a flower. And they negotiate their way through this maze and tangle of leaves and string and everything you can think of. And they don't crash either. Now, they're doing it kind of in slow motion. But other things come to mind, like, for instance, is that bee, this flower is there, it goes to this flower and does its job of pollinating it. But of course, from the bee's point of view, it's getting food. Is this flower, when the bee sees it, is it the same one that I see? Is that the same one? Is it the same thing? Now that in a bit here, that will become important, because that's going to have to do with the codes that we're going to be using when we start particularizing foundation theory in electronics. And we start doing spell checking, only now we're not checking words, we're checking other things. Okay, now before I get to the experiment that finally leads to the networks that we need to look at, let me just mention a few other things. That's particularly since the 60s, we've had a big effort to explain how it is that human beings particularly do the things that they do. The psychologists have come up with theories like, and you've probably heard of these theories, connectionism, okay, and other theories like representationalism. And so there's a big fight going on right now today between those two schools of thought. Connectionism, generally speaking, just roughly uses models like this. The connectionist models are very, very complex. They're difficult to understand just exactly what they're saying, but you can appreciate that if through a network like this and all the weights that you could put into this from moment to moment to moment, that you can recognize words, for example. And that's been the major point of psychology, and the psychology people, psychologists, is to be able to explain how it is that the human being can use language, can use words. You know, and when I say bumblebee, if you'll notice inside yourself, you know, kind of a picture in your mind's eye comes up, just in kind of instantaneously. Not pictures of angels, they fly too. You didn't get that picture, you got a picture of a bumblebee, pretty much automatically. Well, the psychologists, again, you know, use complexity and neural network theory and use models like this to explain the difference between words. And you can appreciate that this can do that. If you make it big enough and complex enough, it can do that. Okay, we want a different way of doing that. What time is it anyway?
10:25.
Yeah, about good time to, got a few minutes here. The psychologists are working on what they're working on, the connectionism, that whole school of thought, and the representationalists, that whole school of thought. If you want a name for a representationalist, that would be Steven Pinker. He's probably the best known. He has a number of books out. If you look on the internet, you'll find all kinds of stuff. As far as connectionism is concerned, I believe her name is Naomi Goldstein. She has a thin book out, very dense, but very good book. If that doesn't have to be the name, email me and I'll email you the info on it. As you can see, I'm not a rememberer of details. Now, neither one of those schools of thought in psychology can come to any definitive conclusions that everybody can believe. You know, and likewise, in the complexity world, they can only come to very simple conclusions. There are a lot of the conclusions are nearly trivial. There's some interesting stuff that comes out of complexity, in the same way that there's real interesting stuff that comes out of chaos theory. But the problem is nothing substantive has happened with chaos, and nothing substantive, really substantive, has happened with complexity theory. And I think most mathematicians would say that. I don't think there's any argument. Everybody on the planet, you know, when chaos was first, quote unquote, discovered, got into the field. And what have they learned since then? Well, not much. There's some interesting stuff, but they haven't really learned much.
It's interesting.
You know, I had last couple of years ago, I taught a integrated science course. And one of the things that I wanted to do was point out to my students complexity, or chaos, I mean. And I wanted to show them what chaos was. Okay, now all of these students had, you know, the prerequisites algebra, so they all know about algebraic functions. Okay, they all know how those graph. You know, they all know how to make a chart, you know, X here, Y there, and you assign a value to X, and then that gives you a value for Y, the dependent and independent variables. Okay, so what I did is on Excel, I made a mathematical function of or a mathematical table of a chaotic function, or a chaotic equation. And that chaotic equation is very simple. And what that thing does is you ratchet through the values that you select, you know, for in Excel, this program that I made. By the way, this program that I made, as far as I know, it's the only chaos program in existence that demonstrates chaos. I couldn't find one on the internet anywhere. You know, I'd have thought they would have had something like that. But anyway, the idea of this thing is that you calculate a value, it takes that last value, and it starts out again, calculates it again, same formula, takes that value, calculates it again. Now, if you put that kind of an equation of y equals x squared, well, it just keeps going, you know, forever. Nothing happens. But you put it into a chaotic equation, and fortunately down there in Kenai Peninsula College, they have some really fantastic electronic stuff for the kids, for the students, you know, and they're kids to me though.
Yeah.
Okay, for the kids, you know, and they have display panels, big display panels that you can write on with electronic pens and everything else. But what happens is you'll be going along, everything will be fine, normal, ordinary algebraic function. Then all of a sudden, this one iteration, blam, it goes off the map. And then one or two iterations later, everything's fine again. You know, and what the hell was that? You know, you can't explain that stuff. And has anybody explained it yet? No. There is no explanation for that. That's what I mean by substantive. Okay, the other thing about, and then we'll take a break, the other thing about complexity theory, that's kind of the proof of the pudding for what substantive has come out of that, is if you take the whole of complexity theory and you translate that to tensor form, and then you start solving those equations, trying to look at what is the geometry of this neural network. What is the geometry there? Well, what do I mean by that? Well, what I mean by that is, you'll remember that I called it recall that I said that the tensors of foundation theory are the same form as the tensors of relativity. They're exactly the same form. They have exactly 256 elements, you know, to these tensors, and they're the same form. Now, the elements of the tensors are not the same, but if you take Einstein's tensors and you want to look at the question of geometry, what's the geometry of space in his case? Okay, then you come up with a number of different possible solutions that doesn't violate the model. Okay, and you could come up with a spherical universe, for example, or you can come up with these weird hyperbolic jobs, you know, these saddle-shaped universes. You can come up with open universes, closed ones, all kinds of geometries. You know, and it's the Minkowski geometries that they're coming up with. You can solve those tensors for geometries. Okay, a mathematician tried that with the variables found, you know, and the functions found in complexity theory, and solved for the geometry of neural networks, which you can do. And his solutions were came to trivial conclusions. Didn't tell you anything. Okay, now, in foundation theory, the solutions are not trivial. And hopefully I'll be able to, I'm not going to worry too much about what the geometry of cognition is. It's fairly complicated, but it is not a trivial solution. And I think you can probably imagine that by just imagining the cognitive topologies. This is changing in time, and it's changing in space, and it's changing in a different way than when we look at our eyeball, outside of our eyeballs, and look at the universe out there. Well, that's got some weird stuff in it too, but this has got some weird stuff in it too, all of its own, that doesn't exist out there, except to the degree that this exists out there. And I don't know, does consciousness exist out there? Where are you going to draw those circles? Well, it's about time for a break, and that's good because I'm dry again. It would be connectionism. Whether you look at any of those fields, we run into some really profound difficulties that's expressed on that bottom equation there, that they do not take advantage of the fact that there's a space variables involved in the way the neural networks are wired. Okay, so somehow or another we've got to figure out a way to get space in there as well as time. Now, by doing this, we can still have all of the power that they have available currently in connection theory and complexity theory, because we can still ratchet time like in a movie. We can still make a frame one after the other, and in fact, neurologically, that's what we do. You have to ask yourself the question, why is it that when we go to a movie and watch one on TV, but better yet, go to the movie, it looks so real, it looks so in motion, when actually, in a movie theater anyway, it's 24 frames a second that's passing you by. It is not continuous, it is ratcheted. In movies come in frames. So do camcorders. They all come in frames. Okay, now this particular equation, when I got the one where I've got the space coordinates in there, you can still do it with that too. Okay, so now we're at a position then to start examining how we get this in there. And the way that I started it was I started with the bugs around my house. And I took a housefly, and in my mind's eye, I took the brain of a housefly, and I took that apart and broke it down into its constituent neurons. Okay, now, fresh from the University of California at Davis, a common housefly has 227,000 neurons. Okay, that makes up the brain of a common housefly. Okay, now just as a, for your information, a common bumblebee has 850,000 neurons, and that's the brain of a bumblebee. Now, when we get up into a bumblebee, keep in mind that we do get into quote-unquote, human-like behavior, in that some bees are aggressive and some aren't. In other words, aggressiveness is starting to appear in something with 850,000 neurons. Okay, compare that to the G5, 158 million transistors. Boy, that puts a bumblebee to shame, but yet the bumblebee puts the G5 to shame. Big time. Okay, so there must be something else going on. Well, rather than dealing with a bumblebee, which is getting to be kind of complex, let's deal with the housefly, which is a lot simpler. 227,000 neurons. Okay, so we pile these neurons on the table, and what I'm going to do in my mind's eye, and what you should be doing in your mind's eye, is okay, now we're going to put together a nervous system. Okay, what the heck do we got here? We've got the individual constituents. Now, let's see what we can do with them. Okay, so I pick up one neuron, and obviously one neuron doesn't do very much for me. You know, that can transmit information from one side to the next, you know, on that behavioral interface model, but it doesn't do much else for you. So what I do now is I pick up another neuron. Now I've got two neurons. Okay, now I can make a simple network, because neuron 1 can connect to neuron 2, and neuron 2 can connect to neuron 1 again. Okay, and by the way, I remembered the words associated with incoming and outgoing signals. In neurobiology, that's called afferent for incoming and efferent for outgoing. Okay, so the efferent wiring on neuron 1 can connect to neuron 2, and the efferent wiring on neuron 2 can connect to neuron 1. Okay, so we've got a simple network. Okay, now neurobiologically, if you look at this, and remember that there's gates in there normally, not a myelin sheath, but whether there's a myelin sheath or not, or whether there's gates or not, it doesn't really make any difference to this nerve spike that's being transmitted, whether this wire is knotted up or crumpled up or anything else. It just doesn't make any difference. It's always going to follow wherever it's going. And it go around loops, it doesn't matter. It's always going to go around and follow that tube wherever it goes. In the same way that electrons in a coax, you know, the same sort of situation. Although, you know, don't confuse neuron wires with coax exactly. It's sort of like that, but not completely.
We're discounting.
Anyway, it doesn't matter which way these things are going, you know, all crumpled up, knotted up. So if that's the case, why don't we, in our mind's eye, straighten all that out, whatever neuron structure we're trying to build, and Cartesianize it. Okay, make something understandable Cartesian out of it. And as a result of doing that, and it's in this particular packet that you'll find these things, is you'll find figures like this. Okay, and then in some of these other packets, there are other figures, you know, that indicate Cartesianizing, and that's all they indicate. But the point is that given the way these things work, the way neurons transmit nerve spikes, it, you know, indicates that you can Cartesianize. And so that little thing that was just done in the mind's eye, you can do things like this. And in the case of these diagrams, you know, I made these things like this. And I put the circles in there. They're perfect circles, and there's no reason why you can't do that. Now this particular leg here, and I call these legs, okay, has a certain length to it. And this particular leg here has another length to it. Now remember, what is it we're trying to do? We're trying to take the equations of neural network theory, the current ones, and we're trying to get this spatial dimension, put the spatial aspect in it, somehow do that. Okay, now we just did an experiment in our minds where we put two neurons together. We come up with these two neurons now that are connected. But because of the way the wiring in a nervous system works, it doesn't need to be as complicated looking as all that. We could Cartesianize the thing, and we can even draw a coordinate system on there if we want to. And let's do that. Okay, now, remember that neurons, like that Purkinje cell that we were looking at, has 80,000 wires coming out of it, and only one neuron connects to one neuron only once. This will happen only one time. This is unique in a biological nervous system. Okay, but just as soon as you do this, Cartesianize, I call it, as soon as you do this, what happened in my mind anyway was this, and this was only, like 2.5 years ago, 3 years ago, whatever it was. I'm doing this in my mind, and when I did that, it hit me, oh, holy mackerel. What is that, except for the neurons? That's the Bohr orbit. That's the Bohr orbit. Okay, now I can I can start writing down equations. Okay, because what's the distance around a circle? It's 2 pi r. And what's the Bohr orbit quantization conditions of quantum mechanics? 2 pi r equals pi lambda, lambda being the wavelength. N lambda, 2 pi r this is the wavelength, this is an integer number, this is the circumference of a circle. Okay, now remember what Bohr is doing. At the center of his coordinate system is an atom, the nucleus of an atom, a positive charge. And then these orbits then will contain a particle called an electron that has been noticed in experiments to be only at certain energy levels. It doesn't exist in a continuum. It exists only at certain energy levels, hence the Balmer lines and all that sort of stuff that you see from spectroscopy. And so that was the problems that Bohr was trying to solve. He comes up with this model of an atom in the middle there at the crosshairs with electrons going around there. And since they are, in his theory, his beginning theories of quantum mechanics, he explains that the reason these energy levels occur is because only certain wavelengths will fit on those orbits. So he came up with a notion that this thing is like a solar system with only certain orbits allowed. Certainly you could have the smallest possible orbit. That would be when n equals 1. And then if you had a whole circle, then only one wavelength of a drawing of a sine wave, only one wavelength would fit. If n equals 1. On the other hand, if n equals 2, you'd have two wavelengths, and that would be an outer orbit and another outer orbit, and finally you get out there to the 8th orbit, and you get into valence electrons, Okay, and then from the valence electrons is where we get in electronics, we get our electrons and holes. It's from that shell of the orbit. And by the way, these make shells. If this is a hydrogen atom, that's all the orbits you got. It's one proton, one electron. Okay, and that is the valence electron. But you get into more complicated molecules or atoms, you know, you have a lot more electrons and you have them arranged in shells. And don't ask me why nature picked on 8, you know, to be quantum mechanically complete, but that's what happened. Those are observations. Okay, that's quantum mechanics, you know, so that's Niels Bohr came up with that. And from that, you know, he came up with a periodic table in chemistry. And so as a result of that, you can go to pretty much any physics, you know, beginning physics textbook or beginning chemistry textbook. And this picture, the picture that looks like this, will be in it. You'll see that picture in pretty much any beginning physics textbook or chemistry textbook. And what they're trying to demonstrate visually is that if that doesn't fit exactly one wavelength or n number of wavelengths on that circular orbit, the wave will destroy itself. Okay, now we know that the Bohr orbit or that notion works because quantum mechanics works. Okay, so we're on pretty safe grounds accepting this equation. Now if we apply it to this little fly network that we just made in our mind, now we have a little bit different situation. We have a nerve spike that can go around in a circle. You know, it can. Okay, there's a pulse there that can go around in a circle. And remember now, the pulse has to be, in this case, one full wavelength on each leg. There has to be that. Otherwise, you don't have information traveling. That would be like taking a nerve spike, and remember what those look like. You have a diagram of that in there. If you break that down into its Fourier components, you can set n equal 1, you can imagine that going around. If you have a full wavelength, you know, in each leg, going from neuron 1 to neuron 2. If you have less than a wavelength, you know, and you try to put that into neuron 1, well, that's not going to work because you don't have a nerve spike anymore. You've got maybe part of one, but you don't have a whole one. If you put too many nerve spikes in there, then you've got an entire nerve spike, but not quite another one. And that will tend to start then buggering up the Bohr orbit characteristics. Now, once you see that, okay, now once you see that in there, then this thing here, of course, is the radius. And I'll speak in VPL about the radius, you know, or the Bohr orbit radius. And that's what I'm talking about in the ENL. You know, just having a wave going around here. And we take the simple case of a wave going around there. Because what we're trying to do now is once we realize, okay, this is the basic, absolutely the basic network that you can make. And once we realize that that is in fact a network that can transmit information around, and it can change in time, and it can change in space, okay, now we're cooking. And now we have a way to get the space variables into the not the chaos equations, but the complexity equations, and hence into the neural network equations. Okay, now they take on a different form. Okay, Okay, now in the case of the neuron, if we are going to be transmitting valid information, we have to have in this case, we have to modify the Bohr equation, and we have to have this. Where n is greater than or equal to 2. In other words, we have to have at least one full wavelength on each leg, okay, and that's the simplest that we can have that exists on this one neural network. Okay, and again, by virtue of the Bohr orbit, you can see that, okay, now here's the possibility of duplicating that in electronics. What's going on neurobiologically, we can duplicate that in electronics. And what we do then is we translate the medium into electrons traveling around in a circle. And in my mind's eye, for me anyway, I have the electrons going this way. Get the electrons. And these are the synapses. That's traditional. There's arrows or synapses. And remember, synapses are not, they're one way. They're not symmetric. And I'll talk a little bit about symmetrical synapses in a minute. Now, in complexity theory and hence neural network theory, they have two different things. They have so-called feed-forward synapses, which is what synapses really are, and they have what's called symmetrical synapses. And in symmetrical synapses, what you would have to do is draw an arrow on both ends. You know, the signal can go either way, but in the real thing, they can only go one way. And in a nervous system, it's potential field effects that are traveling in this direction. Okay, field effects. But they are waves. You know, quantum microwaves, these are waves traveling in this direction, which have to obey the Bohr orbit if you have that kind of a circuit. If they fit exactly on that orbit, you've got a wave, a standing wave. If they don't, they destroy each other. Okay. So there we finally end up now with the idea that we need to translate this into electronics. By the way, I have the electrons going that way so that the conventional current, you know, goes in a counterclockwise way.
And that's called the CNL, right?
Now that's called the CNL. Okay, that's called the CNL because CNL means closed neural loop. And that's the most fundamental and basic piece of a nervous system. One neuron means nothing, but two neurons means something. Okay, now there's an important word. One neuron means nothing, sitting in the middle of the universe. You know, it means nothing. It's just sitting in the middle of the universe. But when you get two together, okay, now you have meaning. And so as a result of that, instead of having an electron going around in a circle as in the Bohr orbit and in the Bohr atom, what I have is information going around, hence those eyes that I like to use. I have information going around, okay? But what that means is, you know, when it goes around and one is communicating with the other, constantly updating itself, what do you end up with? Well, for lack of anything else to call it, keep in mind I have to invent a lot of my words because there are no words for some of this stuff. That I called a minute. A minute.
How do you spell minute?
As in digit.
M-E-A-N-I-T.
Okay, now, you might get an
Coined on the
appreciation
corner
for
of 4th and G.
using this diagram, figure 1.7. Now, this diagram isn't meant to portray this, but if you use this digital diagram, and, you know, my electronics textbooks in the digital area always use graphs like this. And they're all the same amplitude, you know, and they're just digits. So I don't know what, I don't have mine clipped together. What packet is that?
It's in this packet here.
Packet one.
Yeah, that's the packet there, yeah.
Yeah.
There you go.
Oh, there you go, okay. Okay, you can gain an appreciation hopefully for the concept. Okay, now this CNL, we're going to say, what happened in my head is I had that CNL, I realized you could make a Cartesian coordinate system, and you could Cartesianize it. It doesn't make any difference to the neurobiology what shape it is, you know, or, you know, you can just as easily make this. As soon as I drew that picture in my head, okay, then the Bohr orbit. Okay, now it's waves going around in a Bohr orbit. Even in a digital sense, even if you were having digital waves, as in a picture like this, that will only contain, that orbit will only contain certain patterns. It won't contain all of them. There'll only be a certain number it can contain. But it's certainly the case with a sine wave, with a wave. Remember the idea in mathematical physics that this is the same thing as, okay, not equal, it's not an assignation, it's the same thing as. Okay, philosophically you take care of that by making a mathematical universe. That's what's really out there, not the matter, not all that stuff, because we already know that matter, etc., the usual stuff is only about 10% of the universe. All the rest of it, we don't know what it is. So we do things like call it quintessence and stuff like that. So the idea of a mathematical universe is certainly there. In my, you know, justification for the idea is certainly there. My assertion is that if you take the neurons and you replace them with transistors, you can construct the same thing as a Bohr orbit, subject now to this condition. N has to be greater than equal to 2. Or you can, mathematically, you can modify this. You could just say pi r equals n lambda. Now you can start n at n equals 1. However you want to do it. It's just that's just an arithmetical thing. Any other thing that is on that loop now will destroy itself, and you can certainly appreciate that in the Bohr orbit sense. Okay, now my assertion is you can do this with transistors, and so what you end up with in transistors is this. And I want to keep this up because that has to do with some other stuff that's going on, that will be going on. Instead of having neuron 1 and neuron 2 now, the CNL, let's make the electronic counterpart. Okay, now keep in mind, I don't know anything about electronics when I'm doing this. I know a lot more now, but I didn't at the time. Okay, so I'm thinking, okay, neurons provide their own energy. They're cells, after all. They make their own batteries and whatnot. They are a battery. Okay, so that if cell 1 connects to cell 2, which then connects back to cell 1, they're supplying their own power, you know, to do this. Okay, the way I was thinking of doing this is this. And you'll remember the picture of the synapse that I had up on the board. Okay, and you'll remember that synapse was like something like this. Okay, and this area here, the synaptic gap, was in some way modulating the signal from here to here. Somehow it was weakening or strengthening, and that was the conclusion that Hebb came to. Hence, the idea that these things can weaken or strengthen came up in 1948 again with Hebb, and that's why they call them Hebbian synapses. Okay, now Hebbian synapses are not quite what they use in complexity theory and neural network theory. They're doing something philosophically different. Anyway, this thing modulates, in some sense, the strength of this structure. Okay, now doesn't that kind of smell like a transistor to you? You know, doesn't that kind of like a transistor? And in this case, wouldn't you say that this is the base? It's like the base. It's similar to the base of a transistor. Okay, and then the this side, the presynaptic side, remember the signal goes this way, and it's pushing these vesicles down here in the neurobiological sense. So anyway, that's the way information is going. Okay, this is 1, 2. Now it's going this way. Okay, this is going to be like the emitter, like the collector, and then this could be the base, but you have two different kinds of transistors, so it could be vice versa as well. Okay, that's, okay, now, and in a transistor, you know, the base, what's the word?
Modulates.
Well, anyway, it modulates the activity from one side to the other. You know, and in the same sense as what happens in an actual synapse. Okay, so that's where the idea for me came to build this thing, this EML, like this. Okay, and then that's where that figure, this figure came from. Those are supposed to now represent transistors, T1 and T2. And the base, the idea of a base being in there is built right into this picture, you know, drawn into the picture. And it's Cartesianized, and it's got the transistors labeled as T. Okay, what that looks like is, now remember the transistors supply their own energy, but neurons supply their own energy, so they're both, but they're cells, so they are both endothermic and exothermic. They can take in energy, but they can also remove energy. They're self-regulating in that regard. Okay, so in my mind's eye, I'm thinking, how am I going to make a Bohr orbit out of transistors? And the idea that came to my mind was, we'll take two transistors, one here and one here, and if there is energy going into one, then we had better take energy out of the other. Otherwise, any signal going in a Bohr orbit will destroy itself just from energy considerations. You know, it'll burn the wires out. Okay, so one of them has to be an NPN, the other one has to be a PNP. Okay, and so I came up with the notion that this is the NPN up here, and this is the PNP down here. And you do have a diagram of the rest of it in your packet.
Yep. 3.5 is one.
because obviously I can't draw too well on the board. And that's in the same packet this T1 and T2 picture is on, and is figure 3.5. And again, that's in VPL. This comes right out of VPL. Okay, and that thing on the inside there gives you the transistors as they are ordinarily drawn in electronics. And there is your ENL, 1 ENL. And I remember that ENL I have drawn in the patent. It comes out a little bit differently. I have drawn it this way in the patent. The transistors are not drawn electronically, as in that diagram that you have in your packet. They are drawn this way. Okay, this is the base. This is the base. Okay, and then I have this drawn that way. The input signal comes in here, goes out here. And basically, that's the ENL. And what it's supposed to be doing is the same thing as the Bohr orbit. Okay, now as that top transistor, remember, is an NPN, it's taking in energy, and what's happening here is conventional current is flowing this way, and a little bit of energy here. Once there's the proper biasing of the transistors, conventional current will flow across that boundary, go through here and through here. And once it's activated by a signal, for example, and there's an example of a signal in the packet too that you might see and that might activate it. Once that becomes activated, that starts the signal around here. Now again, it's a Bohr orbit situation, so not any signal will exist on that circular path. And I keep drawing it in a circular way all the time because I want to emphasize the Bohr orbit aspect of things as opposed to drawing it in the electronic way, because that's hard to see what's really going on there. Other than drawing it in the electronic way, it's easier to wire, I guess. Okay, now you've got a wave that's going around here. Now, if both of these were NPNs, you would run into the situation of possibly burning out one of these wires, particularly on the emitter side and the collector side. And the way that I have mine rigged up is this is the emitter, and this is the NPN, PNP, and this is the emitter, collector. Okay, so now we have emitter collector circuits. The idea, again, of using an NPN and a PNP is that energy will come in to the NPN, but you can make it so the corresponding energy can exit the PNP. Okay, now one other thing that I did, and this is just to make it more like the CNL. Now remember what this is that we're building an ENL, and we're trying to make it like the CNL. Because what are we trying to do? We're trying to duplicate what the nervous system does. And what does the nervous system do? Well, it does incredible things. You know, like with the bumblebee can recognize the same damn flower that I recognize with my 100 billion neurons, you know, and the poor bumblebee only has 850,000, but yet it can recognize it just as well as I can. And yet, 850,000 neurons can still result in such things as aggressiveness. As opposed to another bee, like the wasps that we have up here, you know, are very docile creatures. You know, they don't bother you, they don't bother me much anyway. And you know, they're very docile, friendly sorts. Okay, now in order to make this more and more and more like the CNL, what I did was I put batteries in here. Okay, and I put batteries in there just to isolate them to one neuron, one transistor or another. So I have batteries, and since this is positive power going this way, you know, in other words, the information now is traveling this way, I put batteries in here. Is that right? Yeah. Okay, now those neurons, those transistors now have a battery hooked to them. So now you've got a neuron, a transistor and a battery, and that becomes very much like a neuron. Okay, that's a model neuron. Supplies its own energy. It modulates, the base modulates a current. So that in this case, especially with the batteries, you can see that a rather small current in the base, given that everything's properly biased, a rather small current in the base will regulate a quite large current in the circle, in the ENL. Okay, and then that thing, then, if those wires are thin enough, should be able to quantize waves. And hence I talk about the CNL being able to quantize frequencies. Now, we can get more into the particulars of this thing, you know, after lunch, but keep in mind, the CNL, we can see where that comes from. It's a fairly straightforward, you know, mind experiment, you know, to put one of those things together. And we can see that that must be the basic, philosophically we can see, because philosophically we can appreciate one neuron doesn't do much of anything, for anybody, you know, or anything. Hence, nature took care of that. Oh, well, what the heck, I'll make 2 neurons, or 3 or 4 or 5 or whatever. Okay, and the true neuron thing then becomes the basic unit of meaning, which then on this thing again is contained information going around, but the whole of it now is meaning that's going around. Okay, what's on that one particular CNL is meaning, and we want to duplicate that in electronics, so we use an NPN, a PNP, we put batteries on them, and now they supply their own energy, and now waves will go around in a circle. And it doesn't matter here either whether the wires are tied in a knot or not. Well, it does, but you know, it really does because of electromagnetic induction, but in principle it doesn't. It's going to follow the wires. It doesn't matter if it's curved. It could be squared off, you know, like they build chips. They like to build chips that way, you know, with squared off wiring. You know, and they can. The only problem with that is at every one of those 90-degree junctions, you're going to get reflections, you know, so you have to worry about that too. But I mean, they have programs, you know, to take care of those kinds of problems, you know, the reflection problem. They have their own methods and techniques. But from my point of view, I just draw them in circles. I draw them that way. In my opinion, they should be built that way. You know, get off that strictly Cartesian and go to something that looks polar. Then they can build stacks of ENLs. Okay, now if you've got, and this one last thing, is remember that thing there, even though now we've got it in the sense of transistors and wires and batteries and like that. Okay, now that thing there still has to quantize, and it still depends on the Bohr orbit radius, which is to say the length of those wires. The length of each one of those legs, pi r, gives us the XYZ that we see up there. Okay, now not just electronics. Okay, foundation theory is way bigger than that. You know, because what this does now is it changes complexity theory, all of it. And it changes, for sure, as a result, neural network theory, all of it. This is a much more general theory. Now, does this idea work? Well, John Pender in Fairbanks, him and his wife are both PhD physicists from Stanford. They attended one of the talks I gave up at UAF, and both agree. They both signed NDAs. They are fully aware of what's going on. They agree with what's going on. John Pender took the circuit that I have in the patent, and that I have included in all kinds of writings that I have. Anyway, took the circuit that I have in the patent application of the ENL and put that into Mathematica. Okay, now he just plugged numbers in for the capacitors and all that stuff, and just plugged numbers in, and he played around with it, and what he found is that, yeah, indeed, you see the spikes where it quantizes, where this thing quantizes in Mathematica. Okay, now what I'm trying to do then is build a macro device that will do that same thing. A nano device will do it for sure, and I'll get into that, but let's do that after lunch. Those are kind of the subtler details, and you know, that's another discussion. The basic idea is, if you could build those wires infinitely small, like the Bohr orbit wires, that would quantize just as well as the CNL just as well as the Bohr orbit quantizes, just as well. The trick is, how big are you're gonna have the wires?
You know, what's the radius for an audio lambda?
How big is this? How big is the audio lambda? It's miles long. Yeah.
Yeah, and how you can get
Yeah,
it
on the
circuit board?
telephone band, which is taken usually to be 300 to 400,000 hertz. So the audio, the voice band on a telephone. Anyway, if you started trying to quantize with a particular radius, you know, the length, the lambda, you know, I think it comes out for 300 hertz or 1,000 hertz, something like it, comes out like 50 kilometers,
Yeah,
you know.
yeah. The lambda and the frequency are reciprocal, and so.
I can. Yeah, sorry about that, I just.
How are you going to get that much transmission line on?
Okay,
a
now those are
circuit board?
those are some of the nuances and details that we need to talk about. You know, how do you get around that problem? Because I ran into that problem, obviously, right off the bat.
First.
You know, good idea, but God, how are you gonna put 50 kilometers of
I
wire
sat
in
in
this
on
thing?
some nanotechnology conferences up in Fairbanks, and they
So
are
let's
doing some
officially
very
break.
interesting work with antennas and